Hi guys, welcome back to Data Every Day. Today we are looking at a data set of restaurant tips, tips that a waiter will get for a given transaction at a restaurant. So we have the total bill, the tips they get, and then some features about the dinner or lunch. And we're going to try to predict the tip that a given waiter will receive at a given meal. So we're going to import NumPy and pandas for working with the data, and then we're going to do some EDA using pyplot and Seaborn. And then for pre-processing, I'm going to use kfold and the standard scaler from sklearn. We'll just use a linear regression model for our predictions today, and let's go ahead and import everything. So we can load in the data using pandas.readcsv, and I'll get the file path up here, tips.csv, just paste it in, and we can take a look. Let me just make this a little bigger. Alright, and here's the data. So we have four text columns, and the other three are numeric. Now this is a categorical column. Actually, I don't know if you call it categorical exactly. It is a count column. It's how big the party was. These are all categorical though, for sure. So let's take a look at data.info. You can see we have no missing values in the dataset, and we have 4 object columns to work with. So we're going to have to encode these object columns in some way. Alright, so let's start pre-processing. And I'm going to do a light pre-processing in this section so that we can do our exploratory data analysis on the data after. So we're going to call a function pre-process inputs that's going to take in a data frame. It's going to make a copy of the data frame, and then it's going to return the data frame. And that's all it will do for now. But now if we call it on our data and store the result in X, X will now be the processed version of the data. Currently it's just a copy, but now we can adjust it. So I'd like to know what kind of values we have in each of these columns. Now, just by looking at them, I can already tell which kinds of columns have an order to their values and which do not. For example, the day column can be ordered because it's days of the week. But I want to know how many values are in each column, because if there's only 2 values, the way we're going to encode it is very simple. So I'm going to create a dictionary that's going to map the column name to the length of unique values in that column for every column in x.columns. And so this will show us the column name and how many unique values are in it. And now I'm not really concerned so much about the numeric values, like total bill and tip, or the size. I really want to know about these ones. So we have 2, 2, and 2. So sex, smoker, and time are binary features. And that makes our job really easy because all we have to do is send one of those values to 1 and the other to 0, and it doesn't matter which we choose. However, the last one, day, this couldn't be considered an ordinal feature. There is a ordering of values between the values in there, and you can see we only have 4 days. So why don't we go and check out what those values are exactly. We take day and we just call .unique to see all the unique values. And we have Thursday, Friday, Saturday, and Sunday. And we want to make sure we order it in that order when we do our pre-processing. So in here, let's start with the binary encoding. So there's 3 binary columns, and I want to take each one and send one of their values to 1 and the other to 0. Like I said, it doesn't matter which one we choose to go to 1, as long as we pick one. So let's start with the sex column, and we're going to call .replace on it, passing in a dictionary. Now the .replace function, this allows us to pass a dictionary with a mapping in it that will map a value to an integer. It doesn't have to be an integer. You can map it to anything you like. But we're going to take, so we know there's 2 values. That corresponds to male and female. So why don't we send female to 0 and male to 1. And that will do the whole binary encoding for us. And I'll do that for the whole column, save it in the column after I'm done. And let's go and do the same thing for smoker. So this is the smoker column. And here the values are different. We know there's 2 values, and they correspond to yes and no. So why don't we set no to 0 and yes to 1. and we'll do it for the last column, which is time. Now time, we can't see the values in here, so let's look at the unique values. We have lunch and dinner. So why don't we send, this is for time, why don't we send lunch to 0 and dinner to 1. Again, it does not matter which you choose, for which. Alright, and now if we run this, you can see the sex, smoker, and time columns have all been encoded as 1s and 0s instead of the text labels. So now for day, we need to ordinal encode. And we can also use replace with the dictionary for ordinal encoding. Especially this is a nice way to do it when you have a low number of values. So, okay, I'll take day and call replace. And now we want to map each of these, can't actually see them anymore. So we have Thursday, Friday, Saturday, and Sunday. And so we want to send Thursday to 0, Friday to 1, Saturday to 2, and Sunday to 3. And that should do the trick. Then the model will now be able to see it as a continuous range of values and as one variable. And let's store that in the column when we're done. Alright, so now you can see those are the unique values, and our data is fully numeric. Alright, so let's do some EDA now. So I'll delete these. Alright, so exploratory data analysis. I'm just going to do a brief rundown of each variable and then see how some of the variables are related. So we'll create a new pie-plot figure with a figure size of 20 by 10. And I want to show each variable in its own subplot. So what I'll do is iterate through a range of length, the number of columns that we have, indexed by I. And for each I, I'm going to create a new subplot in a 2 by 4 grid, 2 by 4, indexed by I plus 1. That's because pieplot requires that the lowest index is 1 instead of 0. Once we have our subplot created, we will call seaborn.histplot. And what we'd like to plot is actually going to be the column, the x.column sub I column. So here is the name of the column, and we're finding the data associated with it. And I'm going to turn on KDE equals true, which is the kernel density estimation, and that will try to plot a continuous function over the histogram, just so we can get a good sense of how it's distributed. And I only want to turn on the KDE for non-binary columns, because it's weird to have I'll actually show you, plot.show. It just looks a little weird when you have these KDEs on histograms with only 2 possible values. So I want to turn them off when we only have 2 values. So we can do this by saying if the length of x evaluated at x.columns sub I, so the ith column, if the length of unique values in the ith column is greater than 2, then we'll keep it with the KDE on, and otherwise we'll do the same thing but with KDE equals false. Alright, and then I just want to put a title over the first one here. So I'll say if I equals 0, so if we're on the first plot, we'll do plot.title column distributions. I didn't spell that right, did I? Distributions. Okay. And here we go. So we can just see how the variables are distributed. Now we only have 2 true continuous variables, the total bill and the tip. All the rest are categorical. You could consider the size as a count column as also numeric, but it is integer, only integers. So we don't get a continuous range like we do for the real number ones. All right, and now I'd like to get some box plots. So very similar. I'm just going to grab this code, paste it down here. Only thing I'll change is that, well, I don't want this these if statements here. I'll change this to column box plots, and I just have to change Seaborn dot histplot to Seaborn dot boxplot, and I'll take KDE equals false out of there. And it tells us we want to make sure we say x equals, so we don't get those warnings. Okay, and so here are the box plots. So these big blocks here are expected, since those correspond to the variables with very few values in them, because we can't possibly have outliers in, for example, these ones. There's only 2 values it could take. However, the ones we should be concerned about are the total bill, the tip, and the size. And you can see we have not really too bad outliers here. The outliers are not so extreme. The whiskers on the box and whisker plot represent sort of the threshold after which you could consider data points as outliers. So this is actually the first quartile. Actually can't see, I think the median might be right up here against the edge. Here, we'll look at this one. This is the first quartile here, this edge of the box. Then we have the second quartile or median, then the third quartile, and then this line is 1.5 times the third quartile removed from the median. This one similarly is 1.5 times the first quartile removed in the opposite direction from the median. And then anything outside of that can be considered as outliers. Now, when you see them all sort of grouped together like this, you don't necessarily have to consider them as outliers, because that could just be a very thin tail coming off and not necessarily something really far away. But if we were to see not such close spacing, if they were all grouped here and then we just had one guy over here, then we might consider removing that outlier, as it could interfere with the data. But it's really up to you how many outliers you want to remove and at which threshold you decide to remove them. Alright, and so we've done most of the univariate analysis that I'm going to do, all of it actually. Now I'm going to move on to the multivariate analysis, which involves seeing relationships between data. So first thing I want to do is take these continuous ranged values, variables, and plotting the points up between them. So we take a training example, we plot its value for total bill against its value for tip, and we do that for all training examples. And that we can do with a Seaborn pair plot, sns.pairplot, and we just want to pass in all the columns that are continuous, which is total bill and tip, total bill and tip. And so here it is. And we can see there does seem to be a positive correlation between the numeric features, and that makes sense. Generally, as the bill goes up, the tip goes up as well. And then for themselves, when plotted against each other, we just see the histograms that we saw above. And I don't really care about doing this for the other features because they're all categorical, so I'll show you what it looks like if you do. It looks a little weird. You just get like rows and columns of data points. Like this. So it's a bit hard to interpret. You can maybe see some sort of positive correlation here, although it's not as nice as seeing it with these. So I'm going to leave it on with just those ones. And then we'll do some correlations. So I want to actually get the Pearson correlation coefficients for each variable against each other variable. So I'm going to create a new pyplot figure with a figure size of 12 by 10. And we'll call seaborn.heatmap here. So I want to get a heat map of the correlation matrix, which we can get with x.core. And I want to turn on annotations so we can actually see the coefficients, and set the minimum value we can display to -1. And I'll give it a color map of Mako. And let's show it. I might as well give it a title as well. Correlation matrix. Alright, and here we can see. So most of the variables are not correlated with each other, but we do have a few. The tip and total bill are correlated with a fairly high positive correlation, and you can see that up here. There is a positive correlation between them. Then day and time is highly positively correlated. And this makes sense, I guess, because people tend to eat dinner more than lunch as it gets deeper into the weekend at restaurants. So maybe on Thursday and Friday, which corresponds to a low value of time, they're having more lunch, which corresponds to a low value of day. And when you get to Saturday and Sunday, which corresponds to a high value of time, you have more dinner, which corresponds to a high value of day. So that's why we're getting a positive correlation here. And then here also, this makes sense, as the size of the party goes up, the total bill goes up, and so does the tip. So, all right, now I guess we'll start training. So we have a good sense of the data. Let's see now. If we just, so I want to create X and Y. We already have X. I'm just going to take off the target column, which is the tip, and store that in Y. So Y is going to be just the tip column. And X, I'm just going to drop the tip column. Alright, so now Y should just be the tips, and X is all the rest of the data. So I'm going to use k-fold cross-validation to evaluate the model today. And the reason I'm doing that is because we don't have that much data here, only 244 rows. So if we did a train test split, we'd be missing out on a lot of training data that we could be using to build the model's performance rather than test the accuracy on. So by doing k-fold, you can evaluate the performance of the model on different sections of the data set without committing to a single test set. So when you're done, you can train it on the whole data set and sort of have a general sense of how well the model will be doing without actually being able to test it on a test set. So let's see. I'm going to create an empty list called results, where I'm going to store the models from store the results of the models from each fold, and then we're going to create our k-fold object, which is from sklearn. We specify the number of splits here, and then it will just let's say 5. Then it will split up the data into 5 different sections, and we can iterate through these sets of indices and train on different sections of the data. So we can iterate through, if we use kf.split on x, if we split x into 5 different sections, then we can iterate through for train index and test index in kf.split. And each time we'll get one of the sections will be held out as the test set, and that will be given by the indices in test index, and the rest of the data will be train index. So what each time I split it, each time I'm working with a different fold of the data, then I'm going to create an xtrain, xtest, ytrain, and ytest. Our xtrain and xtest are going to come from x, and we'll index locate. In the top, we'll use train index as our row indexer, and on the bottom, we'll use test index as our row indexer, and we want to target all columns in x. Then for, oh sorry, this should be xtest, not ytrain, like that. Then for our y's, we'll use index location as well. Up here, we'll index at train index, and down here at test index. All right, and these will be our sets of data that we can use. And then I want to scale the data. So I waited to scale until this point because I only want to fit the scalar to the train set. So this is sort of because you don't want to, it may not be so important here because we are using k-fold, but in general, when you want to sort of see it as a philosophical experiment. When we're working with a train and test set, we sort of assume the test set is not available to us at the time of preprocessing. So we'll only fit the scalar to the train set, like that. Actually, I have to create the scalar, which will be a standard scalar. And the standard scalar will just give each column a mean of 0 and a variance of 1, so that each column takes on a similar range of values, and that can improve the model's performance. So xtrain and xtest are both going to be transformed with the scalar's fit. We'll use scalar.transform. and we pass in xtrain on the top and xtest on the bottom. Now the only problem with this is these will return NumPy arrays, and as soon as we turn it into a NumPy array, we lose the indices, so we will no longer be able to well, it doesn't really matter at this point since we already saved them, but it's just nice if we ever want to deal with them again in a more visual way to turn them back into data frames. So I'm going to do that, and I'm going to set the indices to be the same as they were before, and the column names to be the same as they were before. And on the bottom here, I'll just change these back to xtest. Okay. So we've scaled the data, and now we will fit the data, fit our model to the data. So we'll create a linear regression model for each fold and fit the model to xtrain and ytrain. And then we'll store the result of the fit evaluated on the test set in our empty list up here called results. So results.append, and we're going to append model.score, which returns the r² score for a test set, and we'll pass in xtest and ytest. And r² score is a good way of knowing how the model is performing on a regression task. It measures how dispersed the data is around your fit. So once this is done, finished, our results should now be full of r² values, and I just want to print them out here. Results. And basically I'll just iterate through for I in range length of results. We'll print out the fold number. So fold 1, fold 2, given by the format. I'll format it with I later. And then I will display the r² value to 5 decimal places. So I want to format this with, I'll do I plus 1 so we start at 1 instead of 0. And then I'm going to format this value with results sub I, so the ith r² score. Then once that's done, I'll print out the average r² score. And that will also be to 5 decimal places, and we'll format that with numpy.mean of results. So we'll take the mean across the list. And let me just give that a new line. And there we go. You can see we have varying degrees of success across different folds. And so this may be a problem with just using a test set. Let's say you accidentally picked this as the test set. You would get a very poor performance when really you might be getting something better if you were to use all the data. So the average r² score is sort of a better estimate when you're using such a small number of training examples. All right, and I guess, let me try something. I want to shuffle the data before we do this. It's just good to, I realize I didn't do that because usually the train test split function will shuffle for us. Let's just shuffle with the sample function. And I want to sample 100% of the data, so fraction equals 1.0. And we'll reset the indices after. And drop equals true to prevent the old indices from becoming a new column. And I'll run the whole notebook again. Shouldn't take too long. Just test it. Okay, get the plots. And here, okay, so after shuffling, it looks like our r² score went down slightly. So if we try it again with a random state, let's just do this and shuffle. Yeah, so we're getting roughly about 0.3 to 0.4. So nothing special, nothing great, but we really are working with a very small amount of data here. And I'm also just using one model. I'm sure we could get probably better results if we were to use different models. I'm not sure. You may want to test that out if you want. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.